Hello, welcome to the course Electronic System Design. Last lecture we discussed about the PCB, what is a printed circuit board, and we saw there are various layers on which we lay down the tracks to connect one component into the other one. Today's lecture we will see how these wires look like on a PCB or on a chip, and what are their geometries and how their resistance and capacitance comes into picture, because for connecting a wire from one place to another one, there is a physical resistance of the wire which comes into picture and the capacitance of the wire, and these R and C, these are parasitic in nature. We don't want them, but they are inherently there because of the metal we use. So these resistance and capacitance, how do we calculate for a particular wire, and how do we try to optimize that to get better results? If we have more parasitics, means the resistance is more or the capacitance is more, it impacts the frequency of operation of a circuit. So it is very important to optimize the wires for their capacitance and inductance or resistance, so that we can achieve a higher speed of electronic circuits. So today we are going to discuss what is the wire geometry and what are their resistance, capacitance, and how do we optimize them. So let's start. So let's consider we have a PCB or a substrate. On this we have two wires. So this is your substrate. These are your wires. This is, let's say, wire 1 and wire 2. The thickness of this wire is T from here to here. The length of this wire is, let's say, small l, and the width of this wire is W from here to here, and the spacing between these wires is small s from here to here. So these are two wires where we lay down these wires on the substrate. This substrate can be anything. It can be a PCB or even a silicon substrate. The theory applies to both of them. In similar way, we lay down these wires on PCB as well as on the silicon substrate. We are here considering two wires, 1 and 2. The thickness of the material we deposit, that is the kind of thickness of the wire itself, which is T, small t. L is dependent on the length we need, which is small l. W is the width of the wire, and there is a spacing from the adjacent wire, which is small s. So, now we define some parameter, for example, a pitch of the wire. So, pitch is nothing but the width of the wire plus the spacing in between these two wires. So, that is called the pitch of the wire, that is specified by P. So, here we can say the pitch is W plus small s, and the aspect ratio is T over W. The T is the thickness of this wire and W is the width of this wire. So, this T divided by this W. This is the aspect ratio. In old processes, this aspect ratio, or let us say we call it AR, this AR was very less than 1. However, in modern process, this AR is typically 2. So, this is how the wire actually look like. We have two wires running parallel to each other. So, what is the thickness in between that thickness, the spacing in between, and the thickness of wire? If we both add them together, that is called the pitch of the wire. And the aspect ratio is one important parameter, where aspect ratio is T over W. T is the thickness of wire divided by the width of the wire. In older technologies, where the thickness was normal and we had larger widths, this aspect ratio was very less than 1, because we used the wire of very high thicknesses. W was more. So, AR was very less than 1. However, in modern technologies, we do not have that much of space available to route the wires. We are now going to billions and billions of transistors on the chip. So, we do not have that much space to connect these transistors together. To do that, we have to shrink the width of these wires, so that we have space to route another wire. However, the thickness which we deposit on the material, the metal we deposit on substrate to make these wire, that T we cannot reduce after a certain point. So, T is still significant, and the W has gone very less. So, aspect ratio nowadays is almost 2, which is which was very less than 1 in older technologies. So, this is how a wire look like. Now, let us discuss how the resistance of these wires comes into picture. So for this, let's say we have one wire we need to fabricate that looks something like this. So here we have this wire which is, let's say, 1. This is nothing but a rectangular block of thickness T and the length L, and the width is W. So this is the metal thickness, this is length what we fabricated, and this is the width of the wire we fabricated. So now the resistivity of this material, whatever we choose here, that is rho. So for example, we have rho is the resistivity, which is ohm into meter. So the actual resistance of this block, which is wire number 1, the resistance R is given by rho L upon A. A is the cross section area of this wire, which is nothing but T into W. So this cross section area, so this is T multiplied by W. So we write rho L upon T into W. If we see here in this formula closely, this rho is a constant, and for most of the process this thickness is also a constant. What thickness we deposit generally is a constant for that technology. So this rho and T both are constant, so we can make another constant by combining these, which is, we are calling it rho square into L upon W. So here this rho or this R square is called the sheet resistance. And the unit of this is ohm per square. Here this square is a dimensionless quantity. By doing this, we can now actually count the number of squares to know the actual resistance. If we put L equal to W here, if we put this L equal to W, then this L upon W is nothing but 1. So we can count the resistance by just adding number of squares we have. If L equal to W, then it is like a, we need to just count the number of squares. So R equal to R square into the number of squares. So here we have this wire 1 where thickness is T, length is L, W is the width. So if we put L equal to W, then we just need to count how many squares we have in this length. For example, here if we have W is 1, and if we assume L equal to 3, it means we have 3 squares here in length L. This is, for example, 1, this is 2, this is 3. So we have 3 squares in the length. So the resistance of this wire is going to be only 3 times the sheet resistance of that particular metal, and the sheet resistance is a constant number, as we saw, which is dependent on the resistivity of material, which is fixed, and T is the thickness of material, how much we coat, that is also generally fixed. So we can just count the number of squares and get the resistance of that particular wire. In this case 1, it is 3. However, sometime we want to change the resistance of the wire little bit higher or little bit lower. So that we can do by simply just adding number of wires in parallel. We can reduce the resistance, or in series we can increase the resistance. So for example, we have here this, for example, wire 1. Now we add one more wire in parallel, which is 2. It means this block and this block, now it has lesser resistance, half the resistance than case 1, and if we add two more wires behind them, for example, let us say this is 3 and this is 4. So overall the resistance of this block, 4 rectangular blocks, is exactly same as one rectangular block, because we just added one in parallel and added 2 in series of both of them. So the effective resistance is nothing but R square into 2 length L plus L, which is 2L, divided by 2W, which comes out R square into L upon W, which is similar to the very first one. So here we saw that we can change the resistance of a wire by simply adding the number of squares to it in series, or we can reduce the resistance by adding number of squares in parallel. This is sometimes needed because let us say we need a wire which should have exactly same resistance, but the current driving capability of that component is higher. So we need to have a thicker wire of the same resistance. So what we will do, we will add one more in parallel and 2 more in series, so that this right side block is same in resistance with the first block. However, the current handling capability of this wire is higher compared to the first one. So there are sometime need arises where we want to change the resistance as well from one small value to a higher value, and that is what we can do using this sheet resistance. Now we should know which metals we should use to make these wires. So up to 180 nanometer technology, most wires were aluminum. However, in modern processes often use copper. The problem with copper is the copper atoms actually diffuse into silicon and they can get damaged, they can damage the actual transistor there. So these copper atoms diffuse into silicon and damage the transistor. To prevent it, they must be surrounded by a diffusion layer, diffusion barrier. So for choosing the metal, actually there are so many metals available to us where we can use a metal to connect one component to another component. However, up to 180 nanometer technology, most wires were aluminium because for aluminium the resistance is lower. This was used in older technologies. However, in modern processes, our new technologies, for example, 45 nanometer technology or 28 nanometer technology, in these technology, instead of aluminium, we use copper because the resistance of copper is lower than the aluminium one. However, there is a problem with copper. If we make a track of copper on the silicon substrate, these copper atoms over the time they diffuse into the silicon, and when they diffuse into the silicon they can actually interact with the MOSFET there and they can get damaged by these copper atoms. So this is the problem with using copper. However, to get lower resistance we have to use copper in modern day technologies. So how do we do that? When we make a copper wire on substrate, we generally put a diffusion barrier in between copper track and the substrate so that these copper atoms does not diffuse into the substrate. So this is how we handle the copper on the substrate. However, this discussion we are doing for the on wafer or on chip interconnects. However, the same phenomena these are there on for the PCB substrate. So equal analysis is valid for the PCB and the copper tracks on the PCB. So we need to put a diffusion barrier to prevent copper into diffusing into the silicon. Now let's see some metals and what the bulk resistivity of these metals are. So we know which metal to use for the interconnects. So here we have metal and this side we have their bulk resistivity. For silver, bulk resistivity is 1.6, copper is 1.7, is 2.2, aluminum is 2.8, tungsten 5.3, and molybdenum is 5.3. So these are some of the bulk resistivity of metals what we generally use in semiconductor processes. So these are the metals we use to connect two devices together on a silicon substrate or on a PCB. So now, for example, we have two devices on the same layer and we want to connect them together. So we route a wire from one place to another place, and this wire is made up of, let's say, copper track. However, most of the time, if the circuit is very complex, we have so many components together on the same substrate, then it may be possible that we cannot route the contact from one to another in a single plane. So if the graph is not planar, or we have so many devices so that there is a space constraint, we cannot route all the wires in a single plane, we have to use multiple layers. So for example, metal 1 layer connects some devices some devices which are not possible to connect in metal 1, we connect through metal 2. It means we have to route two wires, one is in the metal 1, and if there is another wire which is coming through which is blocking its path, so we have to take this wire, goes into the layer 2, and there this wire will go through. So this connection between metal 1 and metal 2, this is done using some contacts or vias we call it. So these contacts are nothing but these are some metallic structures which we use to connect two wires. One is the metal 1, one is the metal 2. We dig the hole in between and fill this hole using some metal. That metal can be copper or aluminum. So these contacts or vias, they also has certain resistance. These are because they are smaller in thickness compared to the wire. It means their cross section area is very limited compared to the wire resistance. So these contacts and vias offer higher resistance compared to the wire resistance. So we need to optimize these contact resistance as well. So these contact vias need to be considered very carefully. So contact resistance. In this contact resistance, it's something like this. For example, we have two wires. One wire is in metal 1 layer. So this is, let's say, layer 1. And this is, let's say, layer 2. So these two layers are separated by a dielectric in between. So these are not connected to each other. To make a continuous wire, what we need to do, we have to have certain overlap here between those two. This is the overlap region. And in this overlap region, we dig out certain holes first. For example, this is the hole we make using etching, and once this hole is there, we fill this hole or this gap in between these two layers using some metals. So that there is a contact between layer 1 and layer 2 through this contact. So the current will flow from here all the way through this via and comes to layer 2. So now if you see, the resistance of this wire is, let's say, small r, this is layer 2 is small r. This contact resistance of these vias are significant compared to the layer, because these vias are very small in size, so their cross section area is very small, so they offer much higher resistance. That's why if you see here, we have made 8 vias and they are all in parallel, so that the resistance is less. However, if 8 is not sufficient, for example, on the right hand side, this is layer 1 and this is layer 2. To reduce this via resistance, we have now put 16 vias in parallel. To reduce the resistance. So here we see that contacts and vias also have significant resistance. Typically 2 to 20 ohm, depending upon the technology we use. To reduce the resistance, use many contacts. And we use many small contacts for current crowding around the periphery. So this is how we manage the resistance of the wire. First is, we calculate the resistance through sheet resistance, we count the number of squares and we calculate how many squares are there in total length, and that is nothing but the resistance we can calculate R equal to sheet resistance, which is a fixed value, multiply by the number of squares we have in that length. So, we can reduce number of squares to improve on the resistance. So, that is the wire resistance. However, if we are not able to route the complete wire in a single layer, we need to go for multiple layers or multiple floors. To connect these wires together now, we use contacts, and these contacts are needed for continuity of current. These are very small in size and we need to have more and more contacts for improving on the resistance, to lower the resistance. On the corners, to reduce the current crowding, we need to have multiple wires or multiple contacts together on the corners. So, this is how we calculate the resistance of wire and the resistance of these contacts and vias. Now, let us discuss the wire capacitance, because the capacitance is also important to determine the speed of our electronic circuit. Resistance and capacitance both are important. So, let us calculate the capacitance of wire. So, wire has capacitance per unit length This has capacitance to neighbors and to layers above and below. For example, we have this cartoon of multiple wires running together. So, let us say this is our main wire, which is wire 1. This wire is running around with this wire, which is wire 2. So, 1 is our main wire for which we want to calculate the capacitance. So, on top of this we have layer n plus 1. Our wire is in layer n, and below this we have a layer of n minus 1. So, for example, this is layer 1, this is layer 2, this is layer 3. So, our connection is in layer 2 and we want to calculate the capacitance of this wire. So, the wire has capacitance per unit length we want to calculate. For a unit length, how much is the capacitance? So, there are two components to this capacitance. One is the adjacent to this neighbor. So, this wire 1 has two neighbors, one is on the right side, one is on the left side. These two wires have certain capacitance. Let us denote it by C adjacent here. So, both of the sides this wire has is capacitance C adjacent. That is one component. The other component is the capacitance from the top layer and bottom layer. So, from the top layer, let us call it C top. So C top is the capacitance between this wire and the layer n plus 1, and C bottom is the bottom capacitance of this wire with the bottom layer C bot, which is layer n minus 1. So these are the capacitance component coming around for this wire, and if we write the formula for C total, the total capacitance, so C total is equal to C top, the capacitance with top layer, plus C bottom, the capacitance with bottom layer, plus 2 times the C adjacent, because both of the sides we have C adjacent. So this capacitance and this capacitance we have 2 times. So we have total capacitance C total is equal to C top plus C bottom plus 2 times the adjacent capacitance. This is the total capacitance we have per unit length of the wire. So now we have calculated the resistance of the wire, which we can represent per unit length. So we have the resistance of wire. Now we know the capacitance of the wire, which we can easily calculate by these various component. So whenever we have this R and C component together, R and C, whenever they come together, they make a RC network, which is nothing but introduce some delay in the circuit speed, which is RC, because of the RC time constant of that circuit. So we have here R of the of the wire and C of the wire. So this R and C combinedly gives the in the parasitic resistance and capacitance, and which kind of reduces the speed of the overall circuit. So let's see how we can model the wire in some lumped component or lumped element model to analyze how much delay it causes to the actual speed of the circuit. Lumped element model. So first thing to note is the wires are a distributed system. We are just approximating them using lumped element model. So we have, for example, one R and a C. This we are representing using n segments, where this R is nothing but R divided by n. If we have, let's say, n segments, and this capacitance is also C by n, where n is the number of segments, and we connect n segments together. So for example, this is second segment, where this is R by n, this is C by n, and we connect n such segments. So here we say that these wires are not a lumped element, these are distributed elements. For example, the resistance the wire causes, it's not a single point where the wire having its own all the resistance. This resistance is distributed along the line of the wire. For a very small segment, the resistance is there. So how do we simulate, or how do we analyze the resistance of the wire? We approximate it using lumped elements. These R and C, these are nothing but the lumped element or the point element there. With these we want to mimic the actual wire. So what we do, instead of single resistance and capacitance, we distribute the system over the n segments, and one segment represents a small unit of wire, and we add them together to mimic the complete length of wire. So we are distributing, or we are cutting down this wire in n segments to analyze it properly. However, in actual practice, this resistance has almost like infinite elements, and each element has its own resistance. So instead of infinite, we keep this n to be very large, so that we can mimic the actual behavior of the wire. So this is the n segment display, or n segment consideration of the distributed system. So we have now multiple models available to mimic the wire. Very famous model is the pi model, where we have this R and we have this capacitance, which is C by 2 in the starting and C by 2 in the end. So this is called the pi model. This 3-segment pi model is accurate to 3% in simulation. There are other segments, other models, but they need more segments for same accuracy, and we use this single pi model for Elmore delay calculation. Elmore delay is the to calculate the total delay of the wire, which is caused by putting this wire in the system. How much is the delay this wire can cause? That is called the Elmore delay. and we calculate Elmore delay using the pi model. Now let's see the crosstalk noise which can happen in these wires. So let's say we have two wires which are running close to each other on a substrate. So this is, let's say, wire A, and we have one more wire next to it. This is wire B, and these both wires are sitting on a common substrate. And they have capacitance in between. Let's say this is the capacitance C adjacent, and then we have a capacitance which is C, G and D, we call it ground. Now in this system, the crosstalk can cause noise on non-switching wires. So in this system we have two wires A and B. Let's consider a hypothetical case where A is switching very fast and B is not switching at all. It is at the DC operating voltage, whatever is the voltage, that is constant in B, and only the A wire is traveling, is having some high speed signal going from one end to another end. So this voltage at the A point or A wire is fluctuating very well, and B is constant, and there is a capacitance in between A and B, that is C adjacent capacitance in between, and there is a ground capacitance. Because of these capacitance, there will be a coupling of voltage from one point to another point in B. For example, A is switching fast, this voltage will get coupled to B using C adjacent, and this capacitance, this voltage at A is also coupled to ground using C ground. So this coupling is actually causing noise in the adjacent wires, and that is called the crosstalk noise, which is a undesirable effect, but it is there because of the adjacent capacitance C adjacent and C ground. So let's write it down. These crosstalk causes noise on non-switching wires. If victim is floating, we can model it as capacitive voltage divider. We can draw the equivalent circuit like we have a aggressor, which is our wire A, which is switching at very high speed. Let's say this is our switching source which is causing this switching, and there is a delta V aggressor, wire. This wire is coupled to the next wire, which is our victim wire, or wire B in our case. And the capacitance with ground, there will be a voltage buildup delta V victim in this victim wire because of the aggressor wire, so that we can write the delta V victim So delta V victim is the voltage developed on the victim wire because of the switching, and it can be given by simple capacitive voltage divider as C adjacent divided by C GND plus C adjacent multiply by the delta V aggressor. So here we have the model where wire A is aggressor, which is carrying a high switching signal, but this wire is also coupled with the adjacent wire through C adjacent. Because of this coupling, some voltage will be transferred from the signal from wire A to wire B, and this voltage we can simply write by a capacitor divider rule, delta V victim equal to C adjacent over C ground plus C adjacent into delta V aggressor. So how much is the voltage aggressor is having? If it is, this is higher voltage, this will be coupled to C victim using this formula, and this is called the crosstalk voltage or crosstalk noise. This noise is undesirable, but because of the adjacent wire switching very fast, we have this noise present in the system or in the victim wire. So this C adjacent we want to keep as low as possible, so that there is no crosstalk noise in between these two wires. So we can play around with this C adjacent or the capacitance in between two wire to reduce the crosstalk noise on the non-switching wires. So these are all the aspects we need to understand to make a good wire network in our PCB or on the silicon substrate. So this is all for today. Thank you.